Hello and welcome to the Disruptive Innovation Festival. Thanks for joining this interactive webinar session. The Disruptive Innovation Festival is a 3-week online open access event that inviting thought leaders, entrepreneurs, businesses, designers, makers and learners to explore the question, the economy is changing, what do I need to know, experience and do? My name is Sven Herman and I'm working in the research and analysis team of the LMAC Arthur Foundation, and I'm delighted to have Guglielmo Carra from Arup with me today, talking about growing better buildings. I'll soon head over to Guglielmo, but I'm going to tell you a little bit about him and the session before. Guglielmo is a senior engineer and European technical leader for materials at Arup. He is a material scientist and designer and has a broad experience in structural design, performance assessments, and manufacturing technologies with all kinds of materials, including polymers, bio-based materials, composite systems. He's engaged in particular in helping Arup develop innovative solutions with advanced materials, and one of those we're going to be talking about, which are bio-based materials and actually constructing a facade system from biomaterials. So a little bit about Arup as well. Arup is an independent firm of designers, planners, engineers, consultants and specialists, and they're offering a broad range of professional services related to the built environment. They have been involved in many international projects, including the Sydney Opera House and the Centre Pompidou in Paris. But they're also trying to develop always new and innovative solutions. They're constantly changing the way things are traditionally made in constructions, finding better solutions. And as I was telling you beforehand, today they're going to be talking about one very new and innovative solution, the world's first biomaterial structural facade. And without further ado, I'm going to hand over to Guglielmo now and talking about how to grow better buildings. Guglielmo,
hello,
are you ready to start?
Yep. So many thanks for the introduction, and thanks to anybody that is joining the session today. So let me start with this image. So the starting point of my presentation is the understanding of the fact that the world resources are limited. So it is now understood that the traditional business model, which is linear and based on the constant exploitation of resources, so things are made, are used and disposed, should actually change towards a model which is circular, in which things are regenerated and reused at the end of the life cycle. And that's something that, for example, the energy business already understood many years ago. So when about 25, 30 years ago, the business moved towards, or part of the business moved towards the use of renewable energy resources, such as the solar energy and the wind energy. My point of today is, can we conceive a similar approach in construction and use materials that are renewable and can be regenerated? So can we create high-performance systems and components from abundant resources that we have in nature, such as plants? And when I talk about plants, I don't mean trees, which are usable, of course, but I rather think about plants that grow in our cities and in our farms. So with this idea and with these questions in mind, Arup joined back in 2011 a large European consortium of other 12 large European institutions and companies to actually exploit further and research further with this idea. The consortium, as you can see, is composed by Arup as designers, but then also architects such as the Danish firm 3XN. And together with us, there was a large number of companies involved into the materials development, into the manufacturing, into testing of materials. And this project was aimed to go on for a large time scale, about 3.5 years, with a kind of considerable budget, partly provided by the European Commission. And this fact that the European Commission was keen of funding this project was also giving an understanding of how even high-level institutions really believe that there is room towards the development of more sustainable products and components for building construction. So the aim of this consortium that was called BioBuild, as BioBuild is the name of the project we've been working on, was aiming to design and build 4 building construction systems made out of fastly growing plants. We've been using flax, jute, hemp, sugarcane, so all plants that grow really quickly in short cycles. After 3-4 months, they can be harvested and collected and used to make what? So what we can do out of plants is actually 2 main things. On the one side, we do have fibers, natural fibers, and the fibers can be weaved together to create fabrics. As you see here in my hands, I do a jute fabrics. And these fabrics, technical fabrics, are actually performing really well, and they are comparable to glass fibers, for example, in terms of performance. On the other side, we can get from plants, we can get resins, which are polymers, biopolymers, and there are a wide range of polymers, for example, thermoset, thermoplastic, compostable, biodegradable biopolymers, and of course the selection of these resins has an implication on the technical performance of the resin itself, and also on the opportunity offered by recycling and composting the resin. And the combination of fibers and resin gives a material which is a stiff material, which is called biocomposite. And there are a number of benefits associated to biocomposite materials for construction uses. So that's a lightweight material with a high strength-weight ratio. It can be easily shaped, and of course, it does have a low cost because the raw material used to make biocomposite are actually cheap, as we've seen they come from plants. And if we compare biocomposite to other benchmark materials such as metals, they do have a lower embodied energy, and also they bring the benefit of sequestrating CO2 from the atmosphere, and the CO2 is then embedded into the biocomposite. As you see here, it's a stiff plate. That's a biocomposite plate. Of course, we didn't invent the material itself. We didn't invent biocomposite, since these materials have been used over the past 20 years in other sectors, such as automotive. What we have been doing has been thinking about using these materials at a larger scale in building construction. And of course, this implies the fact that we should be able to improve the performance of these materials, both from a mechanical point of view and from a physical point of view, to make possible that these materials can be used with the very stringent requirements into building construction. So here you see one of the first system that I actually want to show you today, which is definitely the most challenging, is a modular unitized facade panel, 4 meters high, 2.3 meters in width. It's a self-supporting panel designed to achieve high thermal and acoustic performance. If we look at the exploded view of the system, it is composed and it is designed to have 2 skins of biocomposite, one on the outside, one on the inside, connected to a timber frame all around the perimeter of the panel, with thermal insulation in the gap. And the panel itself has also a glass unit. And the particular shape that you see here has been designed, of course, in agreement with the architect, Frixen, and there are 2 main reasons for this very complex shape. On the one side, the idea was to improve the solar gain of the panel by a parametric approach, by modifying the top part of the panel itself. So as you see, there are 2 red dots, and we've been moving these red dots outside and inside the panel. And with a parametric model, we've been calculating and assessing how much light was actually reaching the window. And by doing that and optimizing the shape, we actually optimize the solar gain for the panel for North European countries, in particular we did the simulation for the city of Copenhagen. so that the part which is in shadow through the full day actually fits with the solar and the energy requirements of the building itself. The same approach can be changed for any city worldwide, and this particular effect that we can play with the shape is actually guaranteed by the biocomposite being a material which is easily shaped into any form we might think about. And I will come back to the process of manufacturing of biocomposite later on. On the other side, as I was mentioning, the particular shape of the outer skin was optimized to improve the stiffness of the laminate, so the biocomposite laminate. And we did, of course, some structural calculation, and we proved on paper that the overall deflection of the system was fulfilling the requirements for building construction, even at the local level, with values above L/200, which is the deflection requirements for European systems. Another very particular features of biocomposite is the low thermal conductivity value, which is comparable and even lower than timber. So by using biocomposite, we actually optimize the we reduce the number of thermal breaches into the panel itself. Therefore, the system is performing far below the passive house requirements. The U value total was about 0.38, respect to the 0.8 average for passive house standards. And in this image in particular, you see that for everything that was not related to the shape and the system itself, we've been using, for example, for the interfaces along the edges, we've been using traditional systems, for example, the gasket line and the fixing system with the floor slab, because of course we wanted this panel to be potentially implemented in projects, something that we're still looking for. At the end of the design phase, we entered the manufacturing of the panel. So here you see a few images of the manufacturing process. On the top left side, you see a mold, which is the negative shape of the panel, and that's the place in which the fibers and the resin are placed to create the laminating biocomposite. Then you see a couple of images of the process of laying down the fibers into the mold and the demolding, which is on the bottom right picture. And of course, this process is very labor intensive, so it has been used only for the phase of mock-up for the system. But nowadays, we can of course use processes which are much faster than what we have been doing, therefore improving the speed of construction and also reducing the cost of the system. And here you see the laminate, the external laminate as completed. And it has been a very long process to get to this stage, about 30 months of research together with the full consortium to optimize the performance of the material, to optimize the process, but finally we managed to create this very large outer skin for the panel in biocomposite materials. And we've been using, for this specific case, flex fibers. Here, two images of the mock-up completed. And these represent the first worldwide unitized facade panel made in biocomposite materials. And if you look at the image on the top right, the zoom, you would actually see the very nice texture of the fiber right below the outermost layer of resin, which is a clear resin in this specific case. That's a picture for the interior side of the panel. It has been decided to paint it white, mostly for architectural reason and aesthetic reason. Of course, any color could be used, any coating could be used, but the best from sustainability and a recycling point of view would be to leave the biocomposite completely uncoated. And here on the top level, you see the two brackets for the connection of the panel to the floor slab. At the end of the manufacturing process, we've been entering a phase of testing. Of course, we wanted to prove that biocomposites are suitable for being used in construction. So we have been testing this system according to the European technical regulations. Here you see two images. On the left side is a wind pressure test. So the panel is facing the chamber, and on the inner side of the chamber it is applied wind pressure. And what is very interesting to say is that the overall deflection and the local deflection for the laminate and the panel has been far lower with respect to what we anticipated. So actually the assumption that we made during the design phase for the performance of the biocomposite was actually very conservative. So the material can even do better. We can even think about doing larger things. On the right side, instead, you see water tightness test. We wanted to prove that the material was not absorbing water and that there was no leakage of water towards the interior of the system. Together with this testing, we also perform fire test and durability testing amongst the many other tests we've been doing. And what is interesting is that the fire performance of the panel reached the class B according to the European fire regulations. So it means the biocomposite can be used in facade application and for buildings up to 21 stories in Germany, for example, while in UK would be 18 meters high. And we also exposed and exhibit this system in UK, in London, in March this year to showcase to a large community of people visiting the event the opportunity offered by biocomposite materials. What is very interesting to mention, coming back to the first point about the limited resources available on our planet and the fact that we want to develop materials which are actually recyclable, we approach the design by thinking and the disassembling of the system itself at the very end. So, as I show you here, we thought and we believe that the biocomposite skin can be completely separated from the other components of the systems and separately recycled into the biological cycle, while all the technical components, the metal parts, the fixing systems, the rubber gaskets, they can be recycled separately into the technical cycle. Of course, this point is very crucial. In fact, the biocomposite to be recyclable shall go through a number of checkings, and of course, not all the resins can be recycled. So a proper selection of the resin according to the use into building construction shall be done. I want to show very briefly to you the other three systems we have been developing together with this large unitized facade panel. The first one is biocomposite rain screen cladding, and this shows also the flexibility of biocomposite to be used in a number of applications in building construction. And very simply, you see on the right side the mock-up that we showed at EcoBuild in London. On the left side, the concept of the systems. It works as two components in biocomposite coupled together. On the outside, there is a very large flat panel in biocomposite. In this case, we use a resin called furan, which is obtained from sugarcane waste. So nothing from the plant of sugar is actually trash, but the waste, which is called bagasse, the waste from the sugarcane plant, can be actually used to make a resin. And on the bottom side of this flat panel, there is a stiffening profile still made with a process, a linear production process, still in biocomposite, and these two parts in biocomposite are fixed to a metal substructure, which is needed for fire requirements. The third system, very quickly, is an internal partition kit, is a movable partition system, and again, you see in this image, on the right side, the mock-up as completed, and the exploded view on the left side. In this specific case, we have been using still the same resin obtained from sugarcane and connected to a timber frame with acoustic insulation in the gap. And the use of biocomposite is very crucial because of the structural performance. So with a very thin laminate, we can achieve a very high stiffness, which is needed for impact loads, for example. And at the same time, this particular resin, furan, does have a very low VOC content, which is, of course, very good for the health of for people occupying the building. And the last system that showcased the aesthetic benefits provided by biocomposites is a ceiling system for interior. So here you see a render of the system fixed to the ceiling of the building, and here you see an image of the set of vertical lamellas that can be freely shaped and adapted to any geometry. In this case, we have been using jute fibers. So I move towards the conclusion by saying that nowadays we are, of course, trying to find potential application. Being Arup, a design company and engineering consulting firm, we are looking for potential application together with our clients of biocomposite into building construction. And at the same time, we are looking for opportunities to even extend more the concept of using biocomposite in construction. So we think about the opportunity offered by buildings to grow plants, and these plants finally used for making components. And this brings me to the last slide, which is our vision about how the industry could actually embed biocomposite into the construction process, what we call the urban BioBuild, in which plants can grow into the buildings or at the urban district level. The plants can be taken to make the two basic elements needed for biocomposite fibers on the one side and resin on the other side. The combination will allow us to make building components that can be then used into building itself, and at the end of the service life, they can be either recycled or combusted to allow new plants to grow. With this, I concluded, and I'm ready to take any question, if any. Thank you.
Thank you very much, Guglielmo, for this great presentation, giving us some insights into your system. And I particularly liked the last slide here, to introducing this urban bioloop, which completely in an urban area produces and generates everything for your buildings. So let me just follow up on this with a question. When do you think that would be actually feasible in practice? How do you think, how long does it take until we are actually there and can do this at a reasonable scale?
Well, what we proved into the project is that actually it is doable right now to use plants, of course, to be useful for building construction products. Of course, we've been using plants that do not grow at the moment into the city landscape. We've been using flat jute, and we're doing research now to extend the portfolio of plants that we can actually use. Of course, then regarding, if you're asking me how long it would take for biocomposite products to be used into building construction, that's due to the approval process. So we believe that in some cases, in some of the systems I've been showing you, particularly for interior use, we're very close to application, and we're now working to bring it into buildings in a short time frame of about 1 year.
Wow, that's great. So maybe let's move on to some of the questions from the audience here now. So I've already seen a lot of nice questions. So, but if you have any other questions for Guglielmo, please ask them through the chat function by sending your message to our participants, and we can post them. So I'd like to start out here with a more detailed question, actually, by Miguel. He's saying, "Wow, that's an amazing construction system. And what is the insulation layer actually made of?"
Yep. So we've been, of course, assessing a number of options, and we've been selecting the best option according to us for the embodied energy. And we've been using cellulose fibers, and as well as rockwool fibers. So we did say challenge these two insulation, and of course, it should be said that from a cost point of view, rockwool is much cheaper than cellulose. So of course, we always need to assess together, cost benefits and of course all the sustainability and recycling opportunities. So cellulose and rockwool has been the two choices from our side. And of course, I want to add also that rockwool, that it sounds very, very unsustainable as an option. Instead, is it's offering the opportunity of taking insulation out and reduce it into other construction, into other systems. So it does work.
Mm-hmm. Okay. So, and what do you think in terms of? I mean, you were telling us that most of the stuff can be recycled or can be regenerated in biological cycles. How does it actually look in practice? Meaning, would there additional recycling infrastructure have to be put in place for this to make happen, or how would you imagine those biological and technical cycles coming out of the building materials when it's not used anymore to actually happen in practice?
Yeah. I mean, to happen in practice, of course, we need the full construction change should change. But I think that's the purpose of circular economy as a way of thinking. So, of course, we should move away from the actual concept of using the components and then basically trashing them away. But instead, we really need to put in practice a process in which the components can be separated and recycled according to different cycles, as I mentioned. So the biological for biocomposite and the other components of the system can be reused into for other purposes like metals and timber and so on.
Okay.
Was that the question? Sorry, Sven.
Yeah, no, that definitely answers the question. I think follow up a little bit. So, do you think there would be major additional infrastructure needed to make that happen?
Oh yes, definitely. Of course, there is also an overall understanding of the full life cycle of the products and the system that we use. So, of course, we need also to look at the benefits of the system, not at the very short term, in terms of cost, for example, per square meter, which is of course a parameter that nowadays it is understandable, but it is the major driver for building construction. We should move towards much long-term benefits. So, for example, the overall model from a financial point of view works is, of course, there is a return at the end of the service life of the system in terms of material as a source that can be collected and reused again. Therefore, the initial investment is gonna be paid back at the end of the life cycle as well.
Okay, yeah, that's interesting. It was actually related to a question that Renato was asking. He's asking about the cost viability, whether this is one of the issues, and whether it's still too expensive and needs further development in the market, or do you think it's actually from a cost perspective already feasible now, even if you only look at the actual initial investment cost?
Yeah, no. At the moment, even though the raw materials themselves do cost a few euros per kilo, both the fibers and the resin, at the moment, what is having a large impact on the overall cost of the system is the manufacturing process. So there are not in place manufacturing processes that are such an industrial scale that do allow the system to have a low cost. So just to give you a figure, for example, for the range screen system, the second system I've been showing you, the cost at the moment is about 20% higher than benchmark products on the market. And the reason for that is, as I was saying, to the manufacturing process, which is not industrialized at the moment. It's not comparable to what is ongoing for aluminum, for example, with extrusion and so on. But I think as soon as we would reach a critical mass of products being used in construction, then the cost could really go down and be cheaper than benchmark.
Mm-hmm. So that's really interesting. So you're basically saying the material costs are much lower than for traditional building materials, but to actually produce the actual production step to get to the to get to the final product that you're using in the buildings is still more expensive because it's just not optimized enough, right?
Yeah, that's right. Yes.
That makes a lot of sense. So another question here from Nick. He's asking, have you proposed the structural facade system to any clients yet? And if so, what was their reaction?
Well, I have to say that there is a lot of interest into the architects community regarding the system. We didn't propose the specific system because, as I was mentioning, it has been designed according to a specific expression of 3% as architects. So we've been proposing, of course, the opportunity of using biocomposite. So any architect, any developer willing to make something in biocomposite can, of course, decide on the shape that they want, on the geometry, on the overall design. And of course, biocomposite is a material that adapts to these needs for a particular shape. So yeah, the answer is yes, we're trying to apply biocomposite in construction, but of course, each of our clients does have a specific willing and specific need. Yeah.
Okay, yeah, good. So there's another question from Nick, actually, which goes more like, yeah, more higher level into the general idea how to produce innovation. So he's saying, this is fascinating. This seems to require multidisciplinary teams. What is your experience at working across different disciplines? Do you have any insights in this area? So how can you actually help to produce innovation in this way, and what kind of teams do you need? And can you give any tips on that?
Yeah, that's a very good question that gives me the opportunity also to mention how many people have been actually working on this project. So I've been showing at the beginning the large consortium with 13 European companies involved, but I have to mention that from Arup, about 30 people have been working on this specific project at different times, of course, from different disciplines. So we've been working, I'm part of the materials team, and I've been working together with colleagues from acoustic, from lighting, building physics, structural, facade engineering. So that's definitely one of these projects that, because of the innovation content and also the challenges imposed by applying a new material to construction, of course, needs a strong coordination and a strong cooperation amongst a very wide number of people and skills and disciplines.
So the cooperation between different disciplines and different people is key to actually arrive at those innovative solutions, right?
Yeah, of course. And of course also materials producers, the cooperation with universities to develop the material further has been absolutely crucial.
Yeah, absolutely. Yeah. So coming back to the actual materials, then you're obviously saying they're bio-based materials, so they need space to grow and those kind of things. So what can you say about? Can you maybe comment on like things like competition with food, or the scale of this whole? If you would build all our buildings like this, would that even be possible with the amount of agrariable land that we have available?
Yeah, that's a very good point, and of course we are trying to understand ourselves even more the opportunities. What I can say is that we don't believe that biocomposite used for building construction do necessarily compete with the food industry, because as I was mentioning, we've been using resins derived from waste from sugarcane. So actually biocomposite gives the opportunity of using the large amount of waste which is generated by a number of industry, including the food industry, to actually make something useful. So we imagine a cycle in which, and of course, all the waste is produced also by, for example, food and cutting of trees and so on. And we can think about using that waste that otherwise would be burned straight away or disposed differently. So that's actually our target, to really create an alternative and a useful alternative for building construction with respect to the waste that is produced by the industries.
Okay, very good. So we're slowly coming to the end of the sessions, but we will have time for a couple of more questions. So if anyone has any other questions, please post them now in the chat function. There's one question here from Richard, actually. He's referring to one specific study, maybe you know about it. So he's asking, anyone knows about Grow to Build study, hemp and flax, which has ended this year? Do you know about this study by chance?
Oh, no, I don't. And no, so I'm definitely happy to know more.
Okay, so Richard, in case you have any further information, maybe you can post them or anyone else of our listeners, and we'll put this through. One last question here from Brody. How do these materials compare to conventional materials in terms of length of length of use. So are they as durable as conventional building materials, basically?
Yeah, they could be. Of course, the material used for construction is very recent. So we've been pioneering the use of these materials for construction. So I would say that the time scale up to now is not sufficiently long for us to say with a high level of certainty that these materials are going to last 30, 40 years. What I can say is that through the projects we've been testing the materials for durability, and we have been experiencing by improving the quality of the resin, we've been experiencing an extension of the potential service life. So we believe the materials can actually last for 30 years. Of course, it shall be said that the resin, for example, discolorates through time. So if the willingness of the client, of the user, of the owner of the building is to have a material that remains exactly the same through time, nowadays we cannot ensure that, and there would be a discoloration, a changing lightness and color for the material itself. But from a mechanical point of view, we believe that it could last.
Mm-hmm. Okay, there's another question here from Miguel, actually, and this is, again, related more in detail to, so he's really interested in how you get those materials. So he's saying the fibers obtained from sugarcane waste, for example, and the resin, what is actually the process to obtain the resin, and what is the source for that?
So, yeah, and from sugarcane waste, we've been getting the resin, not the fibers, just to be precise. And it's a process that at the moment, of course, is still an industrialized process. It implies the use of some chemicals, from what I know. I'm not a chemical engineer, so I don't know specifically the full stages through the production of the resin. But of course, the biological content into the resin itself is really, really high.
Okay, interesting. Yeah. So unfortunately, we are running out of time now. But one very last question that fits very well for the end from Nick here is, what are the next steps? Where can I look to hear more about this in future? So how can they stay up to date with what is going on?
Well, definitely as Arup, we are looking forward and doing research at the moment. So as a company, we do have internal research money that in our case, as materials team, we are investing partially into developing further this idea. So we're investigating now for internal research the future opportunities at the urban district level offered by biocomposite. So I invite everybody attending to follow future developments on Arup website. And of course, if you'd like to stay in touch via LinkedIn or any other source, I will do my best to share future news from our side on biocomposite materials.
Great. Thank you so much, Guglielmo, and yeah, thanks very much for your really interesting and inspiring presentation on this new innovation. So we're at the end of this DIF session now, unfortunately, but even though we're in the last week already, there's still plenty of stuff going on. There's still, I think, about 80 sessions still this week. We're having a grand headliner finale tomorrow, actually, the afternoon. So I just like to point to a few DIF sessions that are going on today. In about 50 minutes at 1:30 UK time, we have a session on, do consumers want it circular, which is, I think, a really interesting question, will be a really interesting discussion. Although at 3 p.m. UK time today, we have a session on no business model lasts forever, how you're going to change your business models in the future. And of course, at 5 p.m. UK time, we're having our headline act for today by George Lakoff, the values behind the circular economy. So I'm really looking forward to this one. And if you missed some of our sessions in the last couple of weeks, they're all available for catch up. I'd like to just point you to two of those sessions. One, a headline act that we had last week on the sharing economy redefined. And there was actually another session at the beginning of the DIF by Arup, by Jan Wurm on urban photosynthesis. So if you're interested in what Arup is doing, I would recommend to also rewatch this session. Otherwise, you can join the conversation on Twitter, make further comments on the sessions pages if you have any other things that you'd like to add or any questions to ask. But otherwise, I'd just like to thank Guglielmo again, and also thank everyone for participating in this session. And it's goodbye for now from the DIF. Thank you very much.